Well, good afternoon, everybody. My name is Phil Polstra. I teach at University of Dubuque in Dubuque, Iowa, over in the U.S. And today I want to talk a little bit about fun little USB write blocking devices that you can build for cheap, and hence the title. You can prevent some interesting and exciting moments that you might encounter in your life as a pen tester, and maybe a forensics person as well. So here's what I'm going to talk about, just a little bit, why this talk, what's the motivation for this talk, give you a very brief history of USB and kind of an overview of how it works, and we'll talk about endpoints, descriptors, and then we'll dive down into mass storage devices. How do they work? Once we've covered some of that background, then we'll talk about what can I do in order to keep all my toys? What can I do to block write operations on my thumb drives? And what could I do to have some more fun with USB? So why this talk? Well, USB flash drives have become kind of the de facto standard for people who want to store information, exchange information. You know, in the old days, we had floppy disks and then CD drives and CDs and such. And today, USB thumb drives are pretty much the standard way that people carry things. You know, I know some people have a whole pile of them. They carry around with them all the time. Sometimes they're on lanyards around their neck. So everybody uses these things, and they're very useful to have around, but not a lot of people really understand them. They just kind of treat them as a black box. Now, I don't know how many of you have had this experience, but I've had this happen to me more than once. Someone says, "Hey, Phil, I got this problem with my computer. Can you come help me out?" So Phil pulls out one of his thumb drives with all of his fun tools on it. Maybe it's a Katana installation or something. And I plug it into their machine. Oh, I'm sorry, your machine was connected to our university network. And what happened? The antivirus on the machine detected my lovely tools, but it interpreted them as what? Malware. So a window pops up. Hey, I'm deleting all of your tools. You get to reinstall Katana. Lucky you, right? It kind of sucks, right? Having a way to block that doesn't suck. Other uses of a device like this, if you're doing some forensics, you know, maybe you have a thumb drive, you suspect there's some interesting information on it, you want to look at it, you can't just plug it into a computer, right? What happens? As soon as you plug it into a computer, it's going to update the access timestamps on it. Doesn't matter if you're running Windows, Mac, or Linux, it's going to destroy your evidence. So USB is something that's been around for a long time. 96, they released version 1, and it had 2 speeds it supported, a low speed and a full speed, so 1.5 and 12 megabits per second. A couple years later, updates, some bug fixes. A couple years after that, USB 2.0, which is what most things are running today, and they added another speed, 480 megabits per second. Then 8 years later, USB 3.0, which promises speeds of up to 5 gigabits per second. So how does this work anyway? Well, from a user perspective, they try to make it simple. They try to make it foolproof. From a developer's perspective, it's a little bit more of a pain. All right, so hardware, you know, it's pretty simple, 4 wires. USB 3.0, it's got some more wires, but that's another story. And it's cabled so that you can't do something improper, like connect things that shouldn't be connected. Although if you're doing some development work, then you have to make custom cables sometimes, and it's a little bit of a pain. But and you know, you can have fairly lengthy cables up to as much as 16 feet, it's about approximately 5 meters or so. All right, so software, again, on the software side, they try to make it easy for the user. There's automatic configuration, there's no jumpers, and the process that is used is called enumeration. So basically, you plug in a device, it's enumerated, which means that the host, which is typically a PC, finds out all about the device. And to help with this process, we have standard classes of USB devices. We have human interface devices, printers, audio, and what we're going to talk about today, mass storage. So what happens when you connect this device? All right, so you connect the device, and if you're running Windows, you get the little bing bong and bong bing, depending if you're connecting or disconnecting. And it's a 12-step process. You connect the device, the hub detects the device, your host is informed of the new device, and it determines whether it's low speed or full speed based on pull-up resistors, which one of the data lines it's connected to, resets itself, enumerates itself, and figures out what it can do, assigns it an address, and they start talking. Right? So how does that communication work? How does all that talking work together? Well, it's really all endpoints and descriptors. Right? So endpoints, what is this endpoint? It's a virtual wire. You can think of it as a virtual wire or virtual channel. So it's a unidirectional pipe, right? And the directions are always relative to the host. So if you have an out endpoint, that means your device is actually receiving, right? Stuff is coming out of the host or the hub. And endpoints support fragmentation, just like your network devices would, handshaking and things like that. And normally, this is all done with hardware. You have special controller chips that do all these things for you. You don't have to program your Arduino or something to manually check all this stuff. And when you have an address for an endpoint, the high bit says whether it's in or out. So if it's a 1, it's in. If it's a 0, it's out. 4 basic kinds of endpoints. All devices will have a control endpoint. And for most devices, this control endpoint is how this device is configured, how the device is commanded, it receives instructions and such. Mass storage actually turns out to be kind of an exception to this rule. Unfortunately, it's the most common thing. So of course, the most common device is the exception to the rule. Bulk transport, which is what is used to send commands and data, in the case of thumb drives, interrupt devices or interrupt endpoints, and isochronous endpoints. All right, so control endpoints, mostly used for controlling things, right? And every device has to have at least one control endpoint in and out, usually called endpoint 0. You could, in theory, have more than one control endpoint, but practically speaking, nobody does, right? And it responds to standard requests. You initially connect the device. It doesn't have an address. It's got this generic address 0. Then it talks to the hub a little bit, and it says, oh, now that I know what you are, please reset yourself and take this address, please. Right? Now, if you have a standard class device, your PC is going to say, oh, I recognize this as a HID device, or I recognize this as whatever, and it'll respond to those requests. You can also add to that vendor-specific requests. So we'll see in a little bit, when you connect a device, it will say, oh, I'm this is my vendor, this is my manufacturer, and this is my product ID. And there's some fun you can have manipulating things like that. But all right, so control endpoints, there's 3 stages to these transfers. You have a setup stage where you're identified, you send a command is sent, and then you act the command, and it's an 8-byte request, so it's a pretty quick request. And Sometimes, depending on the command or request, there'll be a data stage, and then there's a status stage. In many cases, you just send a zero-length packet saying, yeah, it's all good. Interrupt and asynchronous. I'm not really going to talk about interrupt. Endpoints are used for things like keyboards, infrequent communications, probably at low speeds. Asynchronous, media, if you're doing multimedia, streaming media, things like that. The nice thing about them is you have guaranteed bandwidth, and the bad thing about them is you don't have as much bandwidth if it's not a non-busy bus. So, bulk endpoints, right? That's what we want to talk about when it comes to mass storage devices. So, what do we know about these? You don't get any guarantees on latency, so you wouldn't use these for media. If the bus is idle, which it probably is, then you get pretty good performance. If there are any other kinds of requests, like an asynchronous, interrupt request, control request, they override any bulk transfers. Right? So you get pretty good performance, but you're also at the bottom of the pile, right? You get lowest priority. You send packets depending on your speeds. Full speed devices have 8 to 64 byte packets. High speed devices are allowed 512 byte packets. And as I said, this is what is used in thumb drives primarily. I sometimes say thumb drives or flash drives, although the same applies to USB hard drives as well. Just that, people tend not to carry those around with them as much, although you could. So we have transactions that consist of, we send a token packet and then some data and an ACK if we're successful. So descriptors, what do? Well, guess what? They describe stuff. So they have a standard format. The first byte says, well, how big is it anyway? Because I'm going to send you a descriptor. You have no idea how big it is in many cases. So first I say, well, this is how big this one is. And then the second byte, I say, well, this is what kind of descriptor it is. And the rest of it is actually a descriptor. So common types of descriptors you get, device descriptors, what kind of device is this? Configuration descriptors, what kind of power does it need, things like that. Interface descriptors, how do I communicate with this device? Endpoint descriptors, what are the channels that this device uses? And then string descriptors, right? Which are just Unicode strings. All right. So a device descriptor looks kind of like this. I'm not going to go over all these fields, but it starts with a length, descriptor type, which is going to be 1, and then it has binary coded decimal for the USB version, which is normally going to be version 2, and it's presented as hex 200. Right? And then we'll have a class, that's that USB device class, HID, mass storage, etc., and a subclass and a protocol. Now, most devices, not all of them, but most of them just put a 0 in here. Right? A 0 means I'll tell you later. Right? I'll tell you later in the interface descriptor. And the reason that they do that is that a lot of devices are what we call composite devices. Yeah, it might be mass storage, but it might be something else. So let's say I have a keylogger. It might be both a mass storage device and a HID device. Right? Hopefully, I have some sort of method to turn off the mass storage device so that I don't plug in my keylogger and people are like, hey, should I mount this device that's logged all my keystrokes? They might get a little suspicious. So, other things in there, manufacturer, product ID, and a serial number. You are required to give a registered manufacturer ID, and the manufacturer can select their own product IDs, and you are required, in the case of a bulk storage device, to provide a serial number, at least the last 13 digits of which are unique, so that there is no other product with that ID and that serial number, the last 13 digits of it, at least. Practically speaking, it seems that most people have all of the digits are unique on the serial number, but I'm sure there's an exception to that. All right, so once your device has been connected, it will get a device descriptor, and then the next thing it's going to do is get a configuration descriptor. And it's going to say things like, how many interfaces do I support? Usually it's just one. What's the configuration value for my default? I can have a string descriptor that describes that configuration. Most of the time this stuff isn't used. The attributes will say things like, am I capable of being remotely woken up? Am I self-powered or am I bus-powered? Right? For our purposes, one thing you should be careful of is the last item, max power. And the reason I say you should be careful is this. You might think, well, I'm going to be lazy. I'm just going to request a lot of power. Guess what happens? You request a lot of power, you have a non-powered bus, and it says, sorry, I can't provide that much power, so your device never enumerates and doesn't work. Right? So usually requesting less than 100 milliamps is pretty safe. Don't request 500 milliamps. That's not so safe. So, interface descriptor will tell you about the interface, and again, as I said, usually this is where we find the class, subclass, and protocol actually input into our machine, our PC. Right? And then the endpoint descriptor, you know, what kind of descriptor is it? What kind of endpoint is it? What's the direction? And what's the max packet size? And the max packet size for bulk storage devices depends on the speed. If it's high speed, then it can be 512 bytes. If it's full speed, it can only be 64 bytes. All right, string descriptor are very basic. It's just a Unicode string. It's a length, descriptor type, and then a Unicode string. One thing that's a little bit different is the string 0 is used to list available languages, and pretty much everybody just says 409, which is US English, which of course is the proper English, right? No. We've had some discussions about that recently. All right. Okay, so let's talk a little bit about mass storage devices in particular. And again, we have flash drives. What kind of hardware do we have for them? Software, etc. How do we talk to them? This picture I ripped off of Wikipedia, so if it looks familiar, that's why. Shows an older style flash drive. You have a storage chip, a flash chip, some sort of controller. Usually there's a crystal, possibly a 12 megahertz crystal. It's pretty common in order to do the appropriate timing for your device. Maybe an LED that blinks. You know, blinking LEDs are always good. It's like, you know, your network interface, right? You like to have the blinking LED because if the LED is not lit, it definitely doesn't work. And if the LED is lit, maybe, right? One thing that was really nice about some of the older drives is they actually had write protect switches. This is fairly uncommon to see now. You can spend a lot of money and get some flash drives that have write protect switches, or you can just do what we're going to do here in a couple minutes. Make your own device and do it for all of them. Okay, typically NAND flash chips are what's used. One of the downsides of NAND flash chips, you only get 10,000 write cycles, which sounds like a lot. It depends on what you're doing with it. Right? If you're putting a cache on a thumb drive, not a good idea. The other thing about thumb drives, they're pretty good on read speeds, and they're pretty bad on write speeds. You might buy a thumb drive and it might say supports high speed USB 2.0. All right. Well, it'll communicate, but it doesn't come anywhere close to writing at those speeds. And it varies from one chip to the next. And typically, the NAND flash memory can only be written to in blocks. You can't just change 1 byte and then write the 1 byte, change the next byte, write the next byte. You have to deal in blocks of data. And those bytes, or those blocks, are typically 512, 2K or 4K. Right? You know, if you did have a device that you were investigating and maybe it was damaged, if you're careful, you can possibly unsolder the NAND flash chips and do a little investigation with those. And you know, you can also use sometimes a JTAG connector if you're familiar with that. So. One thing you should be aware of, by the way, you know, when you buy a hard drive, it says this is a terabyte, but it's not really. You know, it's a trillion bytes. It's not 1024 to the appropriate power. Same thing is true with flash memory. You might think, well, I'm going to come out ahead, but you should realize, depending on the controller chip inside the flash drive, some of them steal a little bit of your flash storage for themselves. Some of them have their own. Right? So what happens? When you plug in your thumb drive, it presents itself to your computer as a SCSI hard drive. And it says, hey, I'm a SCSI device, and I have usually 512 byte blocks. In theory, you can get ones that have 2K and 4K blocks. I have a whole bunch. I have a whole pile of these that I play with at home, and I have yet to find one that didn't have 512 bytes. But I suppose they're out there somewhere. They use what's called a SCSI transparent command set. Usually they're formatted as one big happy partition. Just a little warning to you, or maybe a tip, I guess. Windows machines don't always recognize other partitions, like second or third or fourth partitions. So if you want to hide some information from Windows machines, put it on an additional partition, or if you're investigating a drive, don't plug it into your Windows machine. Plug it into your Linux box. Right? Also, sometimes the report size can be a little bit different for various reasons. You should be aware that a 512 byte block is going to have 16 bytes of error correcting information. So you're still going to lose a little bit there as well. Right? All right, software, usually they have some nice integrated chips that are pre-programmed to do this stuff. I had a thumb drive that went bad, and I thought, yeah, okay, I'm going to take it apart, and I'm going to use pictures of it instead of using the Wikipedia picture for some presentations. I took it all apart, and I found that, you know, it was in this casing. It was about this big, and it was the world's most integrated circuit. The whole circuit was on the little spacer in the USB connector. You know, the backside had the 4 connections, and it was it. It was the whole thing, and I'm like, wow, you know, this is marketing, right? They package it in this big thing, and it's got the sliding thing, and I'm like, wow, it's really just nothing but that. Oops. Don't do that, Phil. Okay. Typically, you get these drives. They're formatted as FAT or FAT32. You can format them as NTFS or something else. There's a lot of choices, especially if you're running Linux. I've seen a couple that come NTFS formatted, but they're somewhat rare. So. All right, so how do we talk to these things? We use this bulk-only mass storage protocol. Sometimes it's called BBB because it's a bulk transport, a bulk transport, and a bulk transport. So unlike typical devices, everything's done on the bulk endpoints. There's 3 phases again. First phase is the command block wrapper phase, maybe some transport, and then command status wrapper phase. And you know, they're pretty much talking SCSI commands inside the command block. So what's this command block wrapper look like anyway? So it sends out, the device sends out this packet, and in there we have a signature. And the signature is just USB-C. It's a USB command block. And then a tag is kind of like when you're doing networking, you have to be able to associate packets together. Well, you have to be able to associate this command with the status that you get back later. How much data you're going to send, is it going in and out? Which of those partitions or logical units is it going to be? And how much stuff are you sending? And then you send the actual command block. Can be as much as 16 bytes and as little as 6 bytes, and it really depends on the command. Right? So what's this command block look like anyway? Well, kind of like descriptors. The first byte is the command. What command is this? Because if I know the command, then I know how long the command is, although in theory I already knew that, but I need to know how to interpret it. So here's just, by way of example, the format unit command. This is a command to atomically just, boom, clear, format the entire unit. It's really convenient if you want to easily clear the entire drive. So it's a good thing to use. And you can see the different things that are in there. Another example, read. There are different kinds of read commands and write commands. This one's called read 10 because it has 10 bytes. Right? It's based on the size of the command. All right, some common commands: format, inquiry, tell me about your device, mode select, here's how I would like to talk to you, mode sense, what kind of mode are you in, and then read, write, send diagnostics, sync my cache, verify my device, and one that sent a lot, test unit ready. In fact, if you connect your device to a machine and you sniff the USB traffic, you'll see a lot of test unit ready, test unit ready, test unit ready traffic. And a lot of devices, if you don't constantly do that, they go to sleep. Right. By the way, a little tip, a good way to sniff that USB traffic, if you're running a Linux box, Wireshark will sniff USB traffic. All you have to do is make sure you enable the USB mod module. Just do a mod probe USB mod, turns on USB logging, fire up Wireshark, all of a sudden you'll see all your USB interfaces appear as something you can capture on. So, all right, and then command status wrapper just tells you, hey, it starts out with a signature USB S. I'm a status wrapper. And then command block, you know, what was the tag and what's the status? And the status is either going to be pass, 0, 1, which means fail, 2, which means phase error, because they're used 2 phases, data 0, data 1. If you got out of sync, you get a phase error. Right. Now, what happens if you send a fail, then the host is going to query the device and say, immediately they're supposed to say, request sense. They're supposed to say, what failed? Please give me the error status. And the reason they do this is historical with the SCSI devices. If you're reading a whole bunch of stuff off your SCSI drive, you just want to know if it's succeeded or not. Sometimes this is called auto sense. It's like, okay, did I get a 0? No, I got a 1. Boom, what was the error? Okay, thanks. Now I'll try to deal with that. All right, so how do I keep my stuff safe? How do I keep my toys? Well, there are a couple of ways that I can block these write operations, right? There are free ways. You know, if I have an old thumb drive or maybe one of the new expensive ones, I might have an actual write protect switch. That's one way. If I want to block write operations on every USB device, be it a hard drive, thumb drive, or whatever, I can enable this key in the registry, right? So it's a free way. And if you're a sysadmin, you might want to do this in an attempt to keep people from sucking information off of your systems. One problem with it, it is an all or nothing thing, right? So you either block everyone or nobody. All right, so non-freeways. You can go buy a commercial write blocker. I found one for about $200, and then I found others that started at $600. I built my device for less than $20. So that's what we're going to talk about now, right? I know what you're thinking. Okay, enough background, Phil. Let's do some fun stuff. Right? Let's talk about microcontrollers. So I want to talk real briefly about what kind of chips could you use. There's a lot of microcontrollers out there. Some of you probably use Arduino. Any Arduino people? Couple? PIC people? Maybe not so much in our community. But Arduinos and the AVR chips, pretty popular. They're cheap. A lot of good community support. Unfortunately, most of them are kind of underpowered for doing USB stuff. You can do some limited device things with Arduinos and their derivatives. I know that Mikhail was doing some talks on that this morning in this very room. And yeah, you can do that, but where they really fall down is on the host side. If you try to use it as a host to connect a thumb drive to, it doesn't work so well. They're usually too slow, 20 megahertz or less. Doesn't work so well. PIC family, also really cheap. It's a little bit of a pain. Some of the newer ones are only available in surface mount technology. And you like to have a nice DIP package you can just plug in to a breadboard and do some work. But again, they don't really have code out there for being a USB host. So my choice was none of those. I chose a microcontroller from a company over in Scotland, FTDI. Some of you may be familiar with this company. The older Arduinos, before the Arduino Uno, used FTDI chips for their USB interfaces. This company they're like the USB people, is the way I would describe them. If it's USB, they're probably doing something with it. So about a year and a half ago, they released a microcontroller that was very USB friendly. It's a little faster than the AVR chips, 48 megahertz instead of 16. A little bit beefier development environment. It's got a real-time multi-threaded OS. Comes with some standard libraries for standard devices such as bulk-only mass storage, etc. Unfortunately, for my purposes, I couldn't use their bulk-only mass storage library because I wanted to hack it, and they only release it as a compiled library. And I didn't want to reverse engineer it and hack it that way. So I ended up re-implementing the entire bulk-only mass storage protocol stack, which was a little bit of work, but it's doable. One thing that is a little different from the AVR packages is that these packages, they come in different pin sizes, and in the AVRs, you have an 8-pin AVR, and it might have so much RAM, so much flash, and then you buy a slightly bigger one if you need more storage. These all have the same. The only thing that varies when you get more pins, you get more I/O pins, and that's it. They have 256 kilobytes of flash memory, which if you do microcontroller stuff, that's huge. And if you don't, you think, is that all? Same thing with the RAM, 16K, which by microcontroller standards is pretty good. It can support 2 USB devices, and they can be either a slave or a host device, or one of each. Also supports other interfacing standards I'm not going to talk about today. SPI and I2C are real popular ones. They have a nice IDE. A lot of development modules are available. Like the PIC chips, only surface mount technology. However, as we'll see here in a bit, they do have nice development packages for people who want to hack them and prototype with them. Right? And they're cheap. Cheap enough that you can take the development board and just embed it in your device later. So they look kind of like this. Basic block diagram. It's probably a little hard to read. You've got your microcontroller over here, and you've got your peripheral buses, your data buses, and your USB host controllers, etc. Here's a screenshot of their IDE. You've got, your code window, file window, and you can do some somewhat limited debugging, but it works. I would describe it as pretty good for small little projects that you're likely to do with a microcontroller, but it's not exactly Eclipse, right? You're not going to develop a whole OS or something in this IDE. Well, more power to you if you want to. But, and they even have a nice little IDE for setting the pins. You can say, okay, this is the signal I want in this pin. For this project, I actually didn't do any of that. All right. So for this project, I have two different packages that you could use. And one of them is nice, and it's really small. And it's their smallest 32-pin chip, which is more than adequate since I'm not using any of the I/O pins. And it has one USB port. Right. So it has one USB port, and the second USB port is connected to these pins right here. Right. So the nice thing about it, it's nice and small. How small is it? It's about that small. All right. And it also is cheap. I think it's about $18 or so. Downside, you have to solder a little bit, but you only have to solder 4 pins. All right, so 4 pins of soldering, not too bad. Especially if you're somewhat skilled at soldering. All right, now if you're phobic of soldering and you just don't want to try that, you can get their Arduino clone. Everyone and their brother is making Arduino clones today. And their clone used to be called the Vincolo. Now it's called the Vinco. I'm not sure why. I think there was some copyright issues or something like that. But it looks like this. All right, so this is their Arduino clone. You'll notice that I can actually, if you're familiar with the Arduino, I can take an Arduino shield and plug it in here. And I also have an extra row of pins here on the top because this chip has more I/O than the Arduino chip does. So I can also get custom shields that work with this that wouldn't work with the Arduino if I want to use the extra pins. The nice thing about this, again, no soldering. It's got a host port and a slave port. I just plug it in, plug in my cable, program it, and then I'm good to go. All right, so what do we do? How does this thing work? Well, we need to block the bad commands that might modify our device. Now, if we were real lazy and we wanted to do this simply, we would just block the bad commands. But, if we all, got those questions right on our CISSP test and such, we know that probably whitelisting would be a better option. It's going to future-proof and it's a little bit easier. It's impossible to predict every possible way that some smart hacker is going to get around it, right? So we whitelist the commands. And so we set it up, and what's this going to look like? Here's kind of a high level of the design. We have one thread, again, it's a multi-threaded OS, that sits on the slave port connected to your PC, and it responds to those control requests and says, hey, I'm here, and I actually fake a device. I say, by the way, I'm a PNY flash drive, and here's my product ID and serial number. I just stole one. All right, I just borrowed a product ID, vendor ID, and serial number from an actual thumb drive. You could set it to something else if you wanted. And then there's another thread associated with the host port, and it sort of bridges commands from your PC over to your actual device, right? And that's sort of the main thread. Now, initially, I did try to, do some caching, and I added extra threads, and it was really cool. And then I ran it up in the debugger, and I found out that I had 12 threads. And I'm like, oh, what do you know? The underlying library from FTDI already did all this stuff. So it actually performed worse, too, because I had threads on top of threads and cache on top of cache, and it all fell down. So I didn't do that in the end. All right, so again, here's our common commands. Which ones do we allow? We allow the ones in red, right? The ones that aren't in red, we say, no, you can't write, you can't synchronize the cache, and no, you cannot format the unit. So I'm waiting in the main thread, waiting for these command block wrapper packets. As soon as it comes in, I call a handler function. I say, hey, is this a whitelisted command? If it is, I forward it to my device, perform the data phase, if there is one, and receive the status wrapper from my device and forward it back to the PC. If it's not, I act the command block wrapper, fake the data phase. Sometimes it might seem a little strange, but some devices get really offended if you report a failure or you don't receive the data. And even if you receive the data and then report a failure, especially a lot of Windows systems, it's like, oh, let me try to write that again. Let me keep trying to write it. It never gives up. So instead, I lie. I just say, hey, it worked. Everything's good. Be happy. All right. So what's the main loop look like in this software? The main loop looks kind of like this. I've got a command, it's in an infinite loop. I read a command into a structure, and then I say, oh, was this a inquiry? Well, then I call a handler for that. Again, I did try to do something a little bit fancier. I tried to make it nice and object-oriented and cool, and then I found that there's just too much variation from one command to the next. And plus, in the microcontroller environment, it ended up not making so much sense. But and the inquiry handler looks kind of like this. I allocate a little buffer, and I forward it to the device, and I get a response from my device. And if I get a response, I forward that to the slave port, and then I wait for a command status from my device, and then I forward that as well. Pretty basic, right? So what's some complications? Windows and Linux treat these things a little differently. One thing about Windows, it tries to autoplay everything unless you have it disabled. The other thing that I've noticed, Linux machines tend to load a lot up front. So you'll notice it takes a little bit longer for the Linux machine when you plug in this device. And again, I lied to it because the Windows machines misbehaved if I didn't. So why would you use this? We already talked about that. You can block writes to your fun drives, or if you're doing some forensics, you could use it for that as well. Again, if you're doing it for forensics, I definitely would recommend you connect it to a Linux box so that you can get those upper LUNs and make sure that you can read every file system that might be on it. Okay, device looks kind of like this. So let's go ahead and I unplugged my device. this replugger. All right, now it'll take a couple of seconds. One thing I should warn you about, you know, in life there are always trade-offs. And one of the trade-offs with this technique, the FTDI chip is only capable of talking at full speed, not high speed. Now we said for write operations, which we're blocking anyway, it doesn't really matter. But kind of the downside of that is even though the write operations don't work anywhere near high speed rates, a lot of these devices, they have to support full speed, but I've noticed that some of them don't support it really well, in that, you know, they go a lot slower than they should when they're operating in that mode. So, you know, it takes, you know, noticeably a little bit longer for devices to pop up and say, hey, here I am. And again, if you're running Linux, the Linux systems tend to take a bit longer because they load everything all at once. Windows systems are a little bit faster about it. So it'll pop up here in a second or so. And here, you know, here's some of the code. Again, all this code is on the conference CD, and if you lost your copy of the CD, just email me or whatever, and I'll get it to you. But, okay, so here's my thumb drive, and let's see what's on here. Trying to think. I think it's Knoppix. Yeah, could be Knoppix. Some live Linux distro. All right, so I'll just pull up this MD5, check some document. So here's my document. And I can come in here and just enter some random junk, all right? And I can save it. And maybe I'll go over here to my Casper directory, or maybe my boot directory, change my grub config file. I don't want to touch it though. It looks so pretty in Kwrite, you know, color coded and everything. But, you know, again, add some random stuff to it and save it. All right. So now if I reopen this, will I see my changes? Yeah, probably will. In this case, because I'm not doing a lot on this machine, right? So it's you'll see that it's still cached. Now, I'm not going to do it, but just trust me, if I unplug the drive and plug it back in and read it, it won't do that. And again, why does it do this? It's because I'm lying to it. I'm telling it, hey, oh, sync, it worked, right? Sure, everything's good. So, you know, it doesn't have to reread it because it has cached it, so it doesn't. All right. Okay, so that's, you know, pretty much the device. And as far as where could you learn some more about this fun stuff, if you're going to do anything with USB, Jan Axelson has a couple books out there. I highly recommend them. She has the somewhat accurately titled USB Complete book, but it doesn't really cover mass storage. So there's another book. You could argue, well, how can you call it USB Complete? It doesn't cover everything, but to be fair, mass storage devices are a pretty big topic of their own. So you can go to the USB organization directly and get some very long, very dry engineering documents. But sometimes you got to go there just because, you know, that's the ultimate authority. If you want to learn more about things like these little FTDI devices and their chips, you can go to their website, FTDI chip. SCSI commands, SCSI commands, you want to get the official references for SCSI commands, you can go to certain places and you can pay ridiculous money for the official SCSI commands. Or you can be like me, and if you're really good at things like Google, you can eventually find out that if you go to Seagate's website, you can get Seagate's SCSI references for free. And do you think Seagate complies with the standards? Yep. So, spend $400, go to Seagate's website. I'll leave the choice up to you, especially if you're just doing these sort of hacking things. Another good resource, John Hyde wrote a book called Embedded USB by Design. It was commissioned by FTDI, and he uses the FTDI chips. He has a really good example of a keyboard logger that you can make with these chips. Also, if you want to get some background on USB stuff, go to YouTube and you can see my 4.4 Con talk from last fall. It's got some good background on that. And again, if you want schematics, source code, whatever, and you don't have it on the CD, email me. There's my email address. You can also reach me on Twitter, just Peepholster. I know it's not real creative, but hey, people find me. So, some real quick lessons learned. Again, sometimes it doesn't pay to be fancy. I tried to add some more threads. Didn't really work out. Tried to make it nice and clean and object-oriented. Also didn't work out. And open source makes the world a better place. My life would have been so much simpler if the bulk-only mass storage library was open source for the chip, and I didn't have to re-implement the whole protocol on top of it. Right. Other than that, any questions you might have, and also don't forget to give feedback for the talks. It helps all of us out. So, any questions? I so thoroughly explained it. It has nothing to do with the after lunch food coma, right? So, you guys don't know this. We're actually conducting an experiment to see, does the food coma effect after lunch increase or decrease if you eat your lunch while standing? Okay. Well, thanks.